So we left off having just explored this idea of this strange little lambda. And if we insert this into our coefficient matrix, just like this, then we have something special happens, and we're able to use that to be able to find our straight line solution. So we're going to get to that. But this idea of the determinant of this particular matrix being set equal to 0, you can write it either like this or like this. And so this way looks familiar. It's basically a modified, what we call a modified coefficient matrix. And this one over here is an alternative way of writing the exact same thing. And you'll notice there's our coefficient matrix. And inside here we're saying coefficient matrix time or minus lambda times I. And that I is not the imaginary I. That's the identity matrix. And if you remember from your matrix interlude notes, that's basically plays the role of 1 in matrix land. So this is like saying A minus lambda times 1. And we're actually going to see how this works. Because if you have your coefficient matrix, whatever that happens to be, minus lambda, which is just some number, times your identity matrix, and this is a matrix, so we give it the bold-face treatment. And your identity matrix, or excuse me, your coefficient matrix is something like A, B, C, D. And your lambda is going to be multiplied by your identity matrix. That's going to have the same dimensions as A. So this one's going to be a 2 by 2 matrix. But the identity matrix is just ones in the diagonal. That's kind of the definition of the identity matrix. So the identity matrix, the way you can think of this is this one has ones in the diagonal and zeros everywhere else. And so you can see there's the ones in the diagonal right there that we're talking about. And so this A, a coefficient matrix minus lambda times this, well, that's the same thing as just lambda here and lambda there when you multiply it through and 0 in the other two places. So this is really the same thing as the matrix A, B, C, D minus the matrix lambda, 0, 0, lambda. And so since these are the same size, the same dimensions, we can do this matrix subtraction and we get A minus lambda, B minus 0, C minus 0, and D minus lambda. And so this really is the same thing as what we were talking about up here, this modified coefficient matrix. Right? And so the key for us here is, what's this all about? It's the lambdas, the lambda values that we're looking for are special numbers. We can find by setting the determinant of this matrix scoot this up, of the modified coefficient matrix equal to 0. And what they're going to do for us is they yield all non-trivial solutions. For the system. And those non-trivial solutions are going to turn out to be the key to finding, key for finding the straight line solutions that we're after. We're on the hunt for the straight line solutions because if we can find these, we can rewrite the entire general solution for the system. So if we can find the straight line solutions, then we can write the general solution. And we can find those straight line solutions by figuring out these lambda values. And that's kind of how this all fits together. So on the next page, one last time, we're going to take a look at our friendly, practically memorized example by now. You've seen this so many times. It's crazy. And if you remember, at this point, we know that the determinant of its modified coefficient matrix, A minus lambda times I, equals 0. This thing, this equation, yields 2 minus lambda times negative 4 minus lambda minus 0 equals 0. This is what we would get if we did that modified coefficient matrix. We did that a couple pages ago. And this, if you kind of multiply it out, you wind up with lambda squared plus 2 lambda. The middle term is 2 lambda. The last term is minus 8 equals 0. And this thing right here has a special name. This is called the characteristic polynomial right there. This guy right here. And I left a lot of space on this page, but this guy, whew, I'm going to draw it down there. That's called the characteristic polynomial for the system. Right? And if you solve that equation, which, I mean, it was already factored up here, you wind up with two solutions. One of them is lambda equals 2 and lambda equals negative 4. These things right here, these guys are known as the eigenvalues. Let me scoot the arrow down here. These are the eigenvalues associated with that coefficient matrix. Every coefficient matrix has eigenvalues. These happen to be the ones associated with this particular coefficient. Right? So down here underneath, note that each coefficient matrix, every coefficient matrix has its own eigenvalues. Now, if you think eigenvalues sounds like a little made-up word, you're kind of onto something. It is from a foreign language, and we're going to talk about what it means, where it comes from here in a second. But for right now, I just want to draw the connection here. So we're setting this determinant equal to 0 because we want to find those particular lambda values that make this true, because those lambda values are associated with the straight line solutions. And we're going to see how they're associated here in a second. And the characteristic polynomial has solutions that are eigenvalues. So on the next page, at the top, remember we started with the assumption that we could write our system coefficient matrix times xy, and that's got to be equal to our special magical lambda values times xy. This equation must be true. This is true for lambda equals an eigenvalue. Right? So in this case, we put this together, we can say our coefficient matrix for our particular situation here looks like this times xy must be equal to lambda times xy. And that means we really have kind of two situations to keep in mind. That must be true for two values of lambda. Lambda number 1, which we'll call 2, and lambda number 2, which we'll call negative 4. So it's got to be true for those particular values of lambda. So let's tease this out and see what happens. So if it's true for lambda equals 2, so if we take a look at for lambda 1 equals 2, we can kind of see how this plays out. Now I'm going to write this equation with that lambda value in there. So 2, 3, 0, minus 4, and xy here. And the other side, that's equal to 2 times xy. Now, this side of the equation is really just saying a constant of 2 times this vector. Over here, this is saying a coefficient matrix times this matrix. But they have to be equal. And what that really means is it really is two equations going on. So this produces a pair of equations. And the top equation is 2x plus 3y equals 2x. That's the top equation. And the bottom equation is 0x minus 4y equals 2 times y. Right? And so let's kind of tease this out and say, well, what happens with this equation? What's going on with this particular equation? For lambda equals 2, these two equations, we can kind of play out a little bit more. We've got an x on this side, an x on that side. Notice the 2x on both sides, those kind of cancel out. And that means the equation is just 3y equals 0, or y equals 0. In the bottom equation, you've got 0x, so that just goes away. And if I combine my y values together, you get another y equals 0. So both of them are telling me the same thing. And if you remember, both say the same thing. And specifically, they give the equation of that straight line solution. Oops, straight line solution from way back. I'm going to see if I can find it by flipping back. It's so many pages ago. Oh, geez. It's way back. Way back at the beginning of this section. We called it y1. It's this guy right here. It's the equation of that straight line solution. It's the equation that it follows. Straight line solution number 1. And that was our pink one. Y equals 0. And they're telling us the same thing. Both equations are telling us the same thing. So what about lambda 2? What about the other lambda value? For lambda 2 equals -4, what happens when we throw that into our matrix equation right here? Well, again, we're going to have 2, 3, 0, -4 times xy. And that's got to be equal to -4 times xy. And what happens? Well, this turns into a pair of equations, a system of equations. The top equation looks familiar, 2x plus 3y, but on this side it's equal to -4x. And then the bottom equation is 0x minus 4y equals -4y. So what happens? Well, the top equation, with a little bit of manipulation, tells us if you put your x's together, kind of subtract the 2x, we wind up with 3y equals -6x, or y equals -2x. And down here, what happens to this equation? Well, you've got 0x, so that's gone, and you have -4y equals -4y. Well, that's just 0 equals 0. So it's not really telling us, this is no new information. But this equation right here tells us what's going on in our second straight line solution. And if you remember, that's the equation of straight line solution number 2. From way back, flip back over here, that's the equation of that blue line. Remember we said, oh, I think it's something like y equals -2x. Well, sure enough, it's right there. It popped up from this magical lambda value, right? So if we know lambda, then you know the direction that our solution is going, our straight line solution. So our equation for straight line solution number 2 was right there. And you'll notice that this thing right here, this provides no new information. It's basically saying 0 equals 0. So it's no help at all. But it's also no hindrance. It's just an absolutely true statement, right? That's all it's doing, is saying true. 0 equals 0. Duh. So for lambda 1 and lambda 2, by plugging those into this equation, we found the direction that those straight line solutions are traveling. So down on the bottom, we're looking for the vector associated with those eigenvalues. And the vector associated with the eigenvalues is given by this direction. So I'm going to add a little note down here underneath this. These directions, I should say direction equations, are really vectors in disguise. Oh, looks like my marker is dying on me here. Ooh, just barely finished. So that one's dead. So it's really a vector in disguise. And so for the when lambda 1 equals, what would you say? Lambda 1 was 2. For when lambda 1 equals 2, what that's saying is you had y equals 0. And that corresponds to a vector that looks like this. Go 1 in the x direction and 0 in the y direction, right? So this is the vector that's telling us go right 1, up 0. So the equation that we found up here corresponds to the vector. And when lambda 2 was equal to negative 4, we got something different. We got y equals negative 2x. And how do we turn that into a vector? How do I express that as an x coordinate or an x direction and a y direction? Well, you basically say if x were to go up by 1, what would happen to the y coordinate? What would happen to the y value? Well, if I put in 1 for x, I get negative 2 for y. So the vector coordinate, or the vector that's equivalent to this, would be 1, negative 2. Or go right 1, down 2. So the equation that we came up with up here turns into a vector that we can use. And it turns out that these guys right here, these things have a special name. Those two are called the eigenvectors associated with the eigenvalues. Lambda 1 and lambda 2. So if you can find the equations using this, then you can find the eigenvectors. Right? Okay, so this is coming together nicely. And on the top of the next page, you'll notice that there's some information. I kind of jumped ahead. This one says for eigenvalue of negative 4. I wound up doing them both here on this page. So at the top of the next page, it basically is just saying do the same thing for lambda equals 2, and you wind up with what you'd expect. Right? Y equals 0. So if we're looking for a vector associated with an eigenvalue of negative 2, we could say, oh, we did that on the previous page. So this guy right here, the thing that we found, this is called the eigenvector associated with lambda equals 2. So this is saying go right 1, go up 0. And the associated eigenvalue looks like this. Right? And so a quick definition of how eigenvectors and eigenvalues fit together. So if you're given a matrix, a coefficient matrix A, and some number, lambda, that's an eigenvalue of A, the only way it can be an eigenvalue is if when you multiply A times xy and you multiply lambda times xy, they are exactly equal. And the key here is that's only true if the vector v, this thing right here, those two coordinates, those two values, are the eigenvector. So we're going to see kind of how this fits together. But the key here is this right here, that central relationship, that must be true for an eigenvalue vector pair. It's got to be true. So this is really just a fancy way of saying we found a way to figure out what are the location of every single one of those vectors that point towards the origin or directly away from the origin, just like we saw earlier on in our diagram. And if you're thinking that eigenvector or eigenvalue sounds kind of like a foreign word, it's true, it is. Eigen is German for roughly translated one's own or one's self. Right? And so an eigenvector is a vector that always points back along itself or points out along itself. and an eigenvalue is associated with that. And we're going to see kind of how they all fit together on the next page. So in the next video, we'll kind of put it all together and see how it all fits together.